Hi guys, thanks for tuning in. In my final video for this chapter, I'm going to talk about differential operators. Now, in my opinion, the best way to introduce differential operators is to go back in time and talk about the calculus course that you already took. So you're already familiar with the notation d dx, and you can think of d dx as a differential operator. You could almost think of it as a verb or a command. Take the derivative of whatever comes after d dx with respect to x. So for example, when you were learning how to take derivatives for the first time, you might have had a function like y is equal to e to the 2x. And when you take the derivative of this function, what you're actually doing when someone says take the derivative, they mean apply the differential operator d dx to both sides of our equation. So that's what I'm doing right here. I'm writing d dx of y is equal to d dx of e to the 2x. Now, d dx is a differential operator that tells us take the derivative with respect to x. Now, d dx of y, we're going to write that as dy dx. And then d dx of e to the 2x, well, it's easier to evaluate the right side of the equation than it is to evaluate the left side of the equation. d dx of e to the 2x is the derivative of the inside times the derivative of the outside. The derivative of 2x is 2, and then the derivative of the exponential is e to that power, so we have 2e to the 2x. Now, once you understand d dx as a differential operator, it can help us understand some other things that you might have encountered in your previous calculus courses. For example, this notation for the second derivative. I remember this notation driving me crazy. F double prime of x I was good with, y double prime, totally fine, but d squared y over dx squared, it never really made sense to me. And the reason was I wasn't looking at this through the lens of differential operators. Now, if we want to compute the second derivative, if we want to compute y double prime, that means that we are taking the variable y and we are applying the differential operator d dx to it twice. So I could rewrite this as, oh, well, if we kind of think about d dx as its own thing, this looks a lot like multiplication here. So we can write d dx times d dx as d dx squared. Now this, is a little bit of a misuse of notation because I'm treating this as multiplication and really, this is more of a composition, but that's how this differential operator notation works, and it turns out to work pretty nicely in this context. Now, if we go ahead and we square d dx, that's d squared over dx quantity squared. And then if we move the y in, just like we do with dy dx notation, we have d squared y over dx squared. And the only part that looks a little bit weird, it's not actually x squared, it's dx quantity squared, but nobody really writes those parentheses down there. It's just assumed that we skip the parentheses down there and understand that to mean dx quantity squared. And that's how you can write second derivative notation in the language of differential operators. Now, once we understand d dx as a differential operator, we could do the same thing with the gradient. So let's think back to this symbol that we know, del, right here. And del is actually a differential operator. It's d dx comma d dy, where we're using partial derivatives for our d's here. So therefore, if we have a function f of xy, the gradient vector is actually a product. It's a product of del times f, or a vector times a scalar. And how do you multiply a vector times a scalar? You distribute that scalar into your vector, df dx comma df dy. So we can understand the gradient in terms of a differential operator. Once we have that, we can start to think about divergence in terms of differential operators. So again, remember that del is equal to d dx comma d dy. And the divergence of a vector field can be defined as del dot our vector field. Watch. If we take del, which is a vector, and our vector field, which is a vector quantity as well, d dx comma d dy dot product with m comma n. Oh, well, we know how to take a dot product of two vectors. It's just going to be d dx times m, d dy times n, or dm dx plus dn dy. And there it is. We can think about divergence in terms of differential operators del dot our vector field. And this is a great way to never forget the equation for divergence. So now we could do the same thing for the rotation of a vector field. So again, if del is dx comma dy, and we have a vector field m comma n, here's how we can define the rotation of our vector field. It's going to be the following 2 by 2 determinant. We put d dx across the top of our 2 by 2 matrix, m comma n across the bottom of our 2 by 2 matrix, and the determinant of that matrix is dn dx minus dm dy. And that's a great way to remember the formula for the rotation of our vector field. Now, just to preview things that are coming later in this course, the rotation of a vector field actually relates to something that we're going to learn about when we move up from 2 dimensions to 3 dimensions in a couple chapters. So suppose we have del as a 3-dimensional vector here, d dx comma d dy comma d dz, and let's embed our vector field m comma n in 3-dimensional space by just throwing a comma 0 at the end of it. That's a nice way to take our m comma n and embed this into 3-dimensional space. The rotation of our vector field is actually the z component of this quantity that relates to differential operators. Look at this. Del is a vector. Our vector field, of course, is a vector quantity. And then between them, I've put a cross product. And it kind of makes sense that that would happen, because if divergence is del dot our vector field, it makes sense that you might ask yourself, like, hey, I know some other operations that I'm able to perform on vectors. Namely, I know how to take the cross product of vectors in 3-dimensional space. So what if we tried that? And it turns out that it works. So if we take del d dx comma d dy comma d dz, and I take my vector field m comma n comma 0, and I apply the cross product here, I'll set up a 3 by 3 determinant. And turns out that because there aren't any z's in m or n, d dz is going to knock out a lot of stuff. And this really simplifies as a result. And so our final 3-dimensional vector is 0, 0, dn dx minus dm dy. And if you look at the end of this expression, dn dx minus dm dy, the z component here is the rotation of our vector field. And that's not by accident. There is actually some meaning here. So the rotation of our vector field is the z component of del cross our vector field. And the reason is you can kind of say, hey, if I have rotation in the xy plane, if I'm rotating in the xy plane, well, you could think of that rotation happening as a swirl around the z-axis. Now, this could happen anywhere depending on how your vector field looks. But the point is that rotation in the xy plane can be expressed as a swirl that's happening around the z-axis. So it's almost like we want to add an extra dimension to start to understand rotation. And that's exactly what's going to happen. Eventually, we're going to learn about curl, and curl is going to happen in 3-dimensional space. So we're going to understand rotation a little bit better in later chapters as we start adding 3-dimensional space into the equation. And then our last idea for this PowerPoint is to talk about the Laplacian. So think about what we've done so far. We've multiplied the vector del by the scalar f. We've taken the dot product of the vector del and a vector field. And we've also looked at del cross a vector field. Here's one more thing we haven't tried. If del is a vector, why not take the dot product of del with itself? So let's try it. So del dot del is going to equal the dot product of d dx comma d dy with itself. And this is very reminiscent of the notation that we saw for the second derivative here. You guys know how to take a dot product. So this is going to be d squared over dx squared plus d squared over dy squared, and we call this the Laplacian. Now, on its own, it's not very interesting. It becomes more interesting when we apply it to a function. So we're going to compute del dot del f, and we'll call that the Laplacian of f. Computing it is pretty straightforward. We just distribute f into that sum. So we get d squared f over dx squared plus d squared f over dy squared. And this is such a special operator that we actually give it its own symbol. So del dot del flips back right side up. This is not a delta. This is the del operator flipped upside down. And now we have the Laplacian of f. Now this all can feel kind of abstract, right? We made up some operator, we applied it to a function, figured out what it would equal, but what the heck is the meaning of this? And that's kind of the last thing that we want to think about in order to try to connect this content to something meaningful. All right, so let's try it out. Let's try to connect the Laplacian to something that we've previously looked at in this video, divergence. All right, so let's say that z is equal to some function f of xy, then the gradient of f is df dx comma df dy, which by the way is just some vector field m comma n. All right, so quite a bit of setup there. Let's see what we can do with this. All right, so the divergence of any vector field is defined to be dm dx plus dn dy. And then in this particular case, m is df dx and n is df dy. So let's plug those in. Okay, so we have d dx of df dx plus d dy of df dy. All right, well, we know how to simplify that. That's not too bad. Oh, that looks like the previous slide. That looks like the Laplacian. We just saw that on the previous slide. So we actually can write this a little bit differently. We can write that as del dot del f, or the Laplacian of f. All right, so wait, what did we just figure out here? Okay, we figured out that the Laplacian del dot del f is the divergence of the gradient field. So remember, with the vector field that we started with, it wasn't any old vector field. It was a gradient field. So the Laplacian is the divergence of the gradient field. And that kind of makes sense with the other material that we introduced, right? Because we already said del dot a vector field is divergence. And we already said that del f is the gradient. So del dot del f should be the divergence of the gradient field. So it all kind of comes together nicely here. Now we want to start thinking about the meaning of that though. Like, what would happen if, say, del dot del f was equal to 0? If the Laplacian was equal to 0, what would the meaning of that be? What does it mean if d squared f over dx squared plus d squared f over dy squared is equal to 0? All right, so in order to unpack what it means for the Laplacian to equal 0, let's just remember what the definition of the Laplacian is. If the Laplacian equals 0, that means the divergence of the gradient field for f is equal to 0. And remember, divergence is talking about sinks and sources, right? That means that we have a vector field with no sinks and no sources. And also, since we have a gradient field, our gradient field is associated to some surface, f of xy, where sinks and sources are correlated with maxes and mins. And so if we have no sinks or sources, we have no maxes or mins. So long story short, if the Laplacian is equal to 0, that means that we have a surface f of xy with no local maxes and no local mins. Now, sometimes I'll have students overgeneralize what this means and say, oh, that must mean that your function f is constant. It must just be some totally horizontal plane without any sorts of bumps on it of any kind. But that's not exactly true. It is not the case that f of x comma y can only be a constant function. There are lots of other kinds of functions that have no local maxes and mins. Let's go to the next slide. We'll look at a few examples and then we'll wrap it up. All right, so on this slide, we could see some examples of surfaces that do not have a Laplacian equal to 0, right? Here we've got a max, down here we've got a min. The surface that I just crossed out does not have a Laplacian equal to 0. Same thing here, same thing here. But there are other examples that do work. So we have 1, 2, 3 surfaces on this slide that have a Laplacian equal to 0. So a constant function is certainly an example. So number 2 right here, a constant function does have a Laplacian equal to 0. But if I tilt this plane upwards a little bit, like number 3, I still have a Laplacian that's equal to 0. And it doesn't have to be linear either. Look at this guy, number 1, also has a Laplacian equal to 0. It's got some curvature to it. It's not constant, it's not linear, but we still have a Laplacian equal to 0 because there are no local maxes or mins on my surface. All right, guys, thanks again for tuning in, and this is the last video for this chapter.